In this video, we are going to talk about exponential functions and some applications on how we can use them. So first, let's define what an exponential function is. So we're going to let b be a constant real number and we're going to have this b be positive and not be equal to 1. Then a function of the form f of x equals b to the x power is called an exponential function. Of base b. So something important to notice about our exponential function is the fact that our base is a constant and our variable is actually up in the exponent. So this is different than our polynomials that had x as the base and had a constant exponent. We have a constant base variable exponent for our exponential functions. And exponential functions are used all over the place for modeling different real-world things. They can model things like population or compounding interest in bank accounts or debt for credit cards for that matter. Radioactive decay can be modeled by an exponential function, spread of a virus, all sorts of things modeled with exponential functions. So they're very important to understand. So we're going to start by graphing an exponential function so we can see what the graphs of these look like. So we're going to graph 2 to the x, and we're also going to graph 1/2 to the x. And I'm going to put them both on the same exact grid. All right, so to figure out some points for this, we're going to start with, here's x, we're going to have 2 to the x, and we're going to have 1/2 to the x. We're going to make a little chart to figure this out. So for my x values, I'm just going to choose -2, -1, 0, 1, and 2, just so I have a few points to plot on here. And I'm going to graph 2 to the x. I'll do that one in red. So I would have 2 to the -2 power, which is equal to 1 over 2 squared. That's 1/4. So at -2, I'm going to have a point at positive 1/4. So that's right around here. It doesn't have to be perfect. 2 to the -1 is the same thing as 1 over 2 to the first. So that's 1/2. So I have a point at -1, positive 1/2. At 0, I get 2 to the 0, which is 1. At 1, I'm going to get 2 to the first power, which is 2. And at 2, I'd get 2 squared, which is 4. If I were to get more points, I would have, when I plug a 3 in, I would get 2 to the third, which is 8, which is way up there. So connecting these points with a smooth curve, I get this is the graph of 2 to the x. Notice that it flattens out to 0 over on this left side, and it grows very quickly, shooting up towards infinity very quickly. Now we're going to do the same thing with 1/2 to the x power. 1/2 to the -2 is 1/2 to -2 like that. That's the same thing as flipping my 1/2 upside down and doing to the positive 2 power. So that's 4. So when I'm at -2, I'm up at 4 for that guy. Similarly, a 1/2 to the -1 flips it upside down to get 2. 1/2 to the 0 is 1. 1/2 to the first power is 1/2. And 1/2 squared is 1/4. So when I connect these with a smooth curve, you get a very similar graph. It's just reflected across the y-axis. This one is 1/2 to the x power. Now, the reason we took our time graphing these two particular exponential functions is because all exponential functions are going to look like one of these two. If you happen to have your base being a number bigger than 1, it's going to look like this red curve. The points will be slightly different, but it's going to have that shape. If you have a number between 0 and 1 as your base, it's going to look like the 1/2 to the x curve. Again, the points will be slightly different, but it's going to have that same shape to it. So in general, what does the graph of an exponential function look like? Well, here's some important facts that we need for it. So here's just a general graph of an exponential function. I'm only going to put one point on the graph right here. This is the point 0, 1, and that is on every single graph unless you're shifting it around somewhere. And that's because anything to the 0 power is equal to 1, except for 0 to the 0, which you'll talk about when you get to calculus. All right, so our exponential functions can either look like this curve. This is b to the x, where b is greater than 1. Or it can look more like the reflected version, where it's going down. This would be b to the x, where b is between 0 and 1. But the graph is very similar on both sides. So things that are always going to happen with our graphs, we always go through that point 0, 1. We have a domain of -infinity to +infinity. I can plug in any x value I want, but my range starts at 0 and goes to +infinity. We have a horizontal asymptote at y equals 0, and that just means it depends on which particular graph we're looking at, but both of these graphs on one of their sides flattens out to our x-axis. That's the line y equals 0. It doesn't ever go past that, it just flattens out to it. So that's our horizontal asymptote. This point 0, 1 is very important. That's going to be on your graph all the time. And when you have something like this red graph, this is called exponential growth. And when it's going down like the green graph, that's exponential decay. So when we talk about things like compounding interest, that's going to be exponential growth. Population is usually exponential growth. Exponential decay would be things like radioactive decay and things like that. All right, so let's do an example where we graph an exponential function, but we graph it using the transformations that we learned about a few videos back. So we're going to graph g of x equals 2 to the x plus 2 minus 1. And the first thing I want to point out is this is going to be like our graph of 2 to the x that we just had, but we're going to be shifting it around using our transformations. So let me quick put my 2 to the x graph back up on here. And I'm going to do it with a dashed line because this is not the one we're actually graphing, but this is the one we just had in the previous example. This is just 2 to the x. So we want to graph 2 to the x plus 2 minus 1. We just have to remember our transformations of graphs. This minus 1 tells us that we're going to go down 1 unit. And this plus 2 up here by my x, that is going left 2 units. So to graph this, I'm going to take every single one of my points and shift it to the left 2 and down 1. So I'm going to start with this point up here at 2, 4. I'm going to move it to the left 2 spots and down 1 spot. And put a point there. My next point is at 1, 2. I'm going to move it to the left 2 spots and then down 1 spot. My point at 0, 1, move it left 2 and down 1. This point that was at negative 1, positive 1/2, move it to the left 2 spots, down 1 spot. So I only really put that one there to try to show what's happening to our asymptote. Our asymptote before was at y equals 0. Since we're shifting down, our asymptote's going to shift down 1 spot as well. So it's going to be at y equals negative 1. So when I do connect this, it's going to flatten out to that y equals negative 1. But otherwise, it has the same general shape. It's just picking up the graph and shifting it around. So this is my graph of g of x that I got just from using transformations from before. Now, you could always just make a table of points, like how we graphed the first ones. But I think it's easier if you already know the basic shape to use the transformations when you can. All right, so now we need to learn about a very particular exponential function that's used all the time in mathematics. And once you get to calculus, it's the most common exponential function that you'll use from that point on. So the function defined by f of x equals e to the x is called the natural exponential function. And this number e right here, it's a very important number in mathematics, kind of like how pi is. This is an irrational number. The decimal goes on forever and ever without repeating. And it is a constant, so it's always going to be the same. And it shows up all the time. This value e, you can find it by looking at the expression 1 plus 1 over x to the x power as x gets really, really big. But that's a little beyond the scope of this class for showing why that's true. But you could plug in really, really huge numbers for x into your calculator, into this thing, and you'll get very, very close to the value of e. E is approximately 2.718. Decimal expansion goes on forever. Now, this e to the x comes up all the time in calculus. And if you actually look at your calculators, whether you're using a graphing calculator or a scientific calculator, you probably have an e to the x button. And that's because of how common that particular exponential function is. So let's learn what we can do with our exponential functions. One very important application is compound interest. So let's suppose that p dollars in principal is invested or borrowed at an annual interest rate R for t years. Then we're going to have three different formulas. One formula, which is not as exciting, it doesn't involve exponential functions, is I equals P times RT. This is the amount of simple interest. So if you just have an account with simple interest, that would tell you how much interest you earn on your account. That's not that exciting though. The ones we care more about are the next two formulas, which we use with compounding interest. So the formula A equals P times 1 plus R over N to the NT power. This is the future value of the account after T years with N compounding periods a year. So what is a compounding period? That's just how often they're calculating your interest. So if you have an account that's compounded monthly, then 12 times a year, they're going to calculate what the interest is and add that to your account. Our other formula is A equals P times E to the RT. This E is that same E we just talked about, our natural exponential function. So we have this is the future value after T years when it's compounded continuously. So when you see compounded continuously, the way you can think of that in your head is it's compounded infinitely many times a year. So rather than compounding it every month or even every day or even every second, it's being compounded way more than that. As soon as it's calculated, it's already out of date again. So compounded continuously is infinitely many times a year. Let's do an example using our compound interest. We're going to compare all these different types of compounding in this problem. We're going to suppose that $8,000 is invested and pays 4.5% per year. Determine the amount in the account after 5 years compounding. First, we're going to do annually. Then we're going to do quarterly, monthly, daily, and then lastly, continuously. So we're going to do this problem with 5 different kinds of compounding. So we're going to have basically 5 examples in one. So before we go ahead and calculate this, let's think about what all the variables in our formulas are going to be. So for both of the formulas, this 8,000 right here, that's going to be our P. That's the amount that was being put into the account initially. It's our principal. This 4.5%, we would write a 0.045. That's our R. That's our interest rate. What is this, 5 years? That's my T, the number of years. And then I just have to figure out Well, we have everything we need for the continuously formula. That's just P times e to the RT. But for these ones, I have an N that I need. So remember, N is the number of compounding periods a year. So annually just means once a year, so N is 1. Quarterly, 4 times a year. Monthly, 12. And daily, we will use 365, since there's usually 365 days in a year. So then again, this continuously uses the other formula, so we don't have an N. Now it's just a matter of plugging all this info into the formula. So let's do annually first. We're going to use the formula A equals P times 1 plus R over N to the NT power. And we just fill in all the info we have. So I'm going to have 8,000 times 1 plus 0.045 over 1 to the 1 times 5 power. And at that point, you can actually go ahead and type it all in your calculator carefully. You have to be careful with parentheses, make sure you get it typed in correctly. But if you type it in correctly, you're going to get $9,969.46 when it's compounded annually. Now let's do quarterly. For quarterly, we're going to use that same exact formula, but the only thing that's going to change is the N. Everything else is the same, but my N, since it's quarterly, is 4. So you would type all of that into your calculator very, very carefully, and you will get to the nearest penny, $10,006. So far, let's take a look at what we got. We compounded more times a year, and we ended up with more money. Not a lot more, but it is a little bit more money. I wonder if that's going to continue. Let's see what happens with monthly. Based on our observations on these first two, we would guess that monthly will get us even more money than what we got with quarterly. Let's see if that works. So with monthly, that's using N equals 12. So you would type all of that into your calculator and get $10,014.37. So far it is working the way we thought. Monthly gave us even more money than quarterly. Not a lot more, but about $8 more. $8 is $8. You might as well take it, right? Now let's see what happens daily. If it's compounded daily, if our hypothesis holds here, we should have even more money in the account. Let's check. I would have 8,000 times 1 plus 0.045 over 365 to the 365 times 5 power. Type all of that in carefully, and you will get $10,018.44. So yes, we got even more money compounding daily. So now, the only one that we have left to calculate is compounding continuously. And remember, that one uses a different formula. But I also said compounding continuously is like compounding infinitely many times a year. So if it follows the same pattern, that one should get us the most money we can possibly get with this particular interest rate. So let's see. Even though it uses a different formula, see if it works that way. So remember the continuously formula, A equals P times e to the RT. So I would plug in my 8,000 for my P again. My rate is still 0.045, and my T is still 5. So I would type that into my calculator, and you get to the nearest penny $10,018.58. So that one's not a lot bigger than daily, but it is still bigger. You're still making a few more pennies over there. So yes, the more times a year it's compounding, the more money you're going to get. And what this means is, let's say you're investing money somewhere and it has the same interest rate at two different places. If one of them compounds more times a year, put your money there because you're going to make more money off of it over there. And of course, if we're talking about debt, you want it compounded less times a year if possible so that your debt doesn't grow out of control either. All right, let's do another application of exponential functions. We're going to talk about half-life. The half-life of a radioactive substance is the amount of time it takes for half of the original amount to change to something else. Or how much time it takes for half of it to decay. So using the half-life and exponential functions is how we do carbon dating. So figuring out how old various things are based on the amount of carbon that has decayed. So this has a lot of applications in the sciences. Let's do an example with half-life. So we have cesium-137 has a half-life of 30 years. In a sample originally having 2 grams, the amount A of t left after t years is given by the formula A of t equals 2 times 1/2 to the t over 30 power. How much in grams is present after 30, 60, or 90 years? So we're going to actually use the formula to do this, but you could figure it out just by thinking about the definition of half-life. Remember, half-life is the amount of time it takes for half of the material to change to something else. My half-life is 30, so after 30 years, I should have half of my original amount. So instead of 2 grams, I should have 1 gram. But let's use the formula so that we get our practice using an exponential function. So we had A of t equals 2 times 1/2 to the t over 30 power. And we want to first figure out what happens at t equals 30 years. So after 30 years, what happens to our 2 gram sample? We would have A of 30 equals 2 times 1/2 to the 30 over 30 power. Well, 30 over 30 is 1. So this is saying 2 times 1/2 to the first power. 2 times 1/2 is 1. So we would have 1 gram. This is exactly the definition of half-life. Once the half-life has occurred, you have half of the material left. Half of my original amount is just 1 gram. Now, what do you think is going to happen at t equals 60? That's another 30 years has gone by. Well, in theory, this 1 should be chopped in half. We should have another half die, and so that's going to make it down to 1/2 gram. So it keeps getting chopped in half. Let's see if that works. A of 60 would be 2 times 1/2 to the 60 over 30 power. Now 60 over 30 is 2. So I have 2 times 1/2 squared. 1/2 squared is 1/4. 2 times 1/4 is 1/2. So I have 1/2 gram left after 60 years, which is exactly what we thought would happen. We had another half-life go by, so another half of the material disappears. Our last one to check was T equals 90. So that's another 30 years. That's another half-life. So we should expect that half of this material will disappear, which would put it down to 1/4 of a gram. And we'll check with the formula to make sure that happens. A of 90 is 2 times 1/2 to the 90 over 30 power. 90 over 30 is 3. So I have 2 times 1/2 to the 3rd. Well, 1/2 to the 3rd is 1/8. And 2 times 1/8 is 1/4 grams left. So again, it got chopped in half again. Every 30 years, that amount is going to get chopped in half. All right, so those are just a couple applications of exponential functions. As long as you know how to type it into your calculator and what it means, then you're okay with all sorts of applications once you have the formula. So just remember what the basic shapes of exponential functions look like. Remember that the base is a constant and the variable is an exponent, and you should be in good shape on these. If you have any questions, feel free to drop them below, or you can come to office hours or email if you're one of my current students. Come back for our next video where we'll talk about the inverse of these exponential functions, which is the logarithmic functions. So I hope to see you for the logarithms that we get in our next video.